last time we talked about the Ising transition based on this kind of a toy model, infinitely long-range Ising model, and we use kind of a exact method which is based on the steep descent approximation, which becomes exact in the thermodynamic limit, and we show that there is no phase transition at finite temperature, and there is a phase transition, zero temperature and zero field. And based on this kind of exact solutions, we could access to the critical properties by expanding the free energy near this critical temperature. Sorry, let me correct the statement. We find that there is a phase transition at finite critical temperature, and then we expand this free energy close to this phase transition point, and we get these exponents, which I just mentioned at the end of the lecture last time. So today we will use a different but closely related method, which is the mean field theory, which is the more realistic Hamiltonian of an Ising model in D dimensions. And this is the Hamiltonian that we introduced many times. And at zero coupling, suppose there's just no spin-spin interactions, then we could calculate this partition function pretty straightforwardly, which is nothing but the Zeeman term acting on the local spin. And this is 2 hyperbolic cosine of h over kBt, where h is the external field to the power of n, and we take the derivative of the mean field, the free energy is back to the field. You get a paramagnetic response of magnetization to the external field, which is hyperbolic tangent h over kBt, which has been known in your thermal physics or solid state physics. So this is just a bunch of the free spin which are not interacting. But once we introduce the Ising coupling J, which is finite, then we are able to calculate this magnetization based on the approximation called the Weiss mean field. Okay? So in essence, each of the spin on every site experience the so-called effective spin coming from the neighboring sites. So because in this nearest neighbor Ising model, we have a coupling J, which is the spin-spin coupling between site I and I plus 1. We also have spin-spin interaction between the other neighbors I and I minus 1. And this is a D-dimensional cubic lattice, for example, over there. And you could pick up the so-called effective field, which includes the external field that you applied, as well as the effective field coming from the Ising coupling of the neighboring spins. Okay? So in other words, each spin feels or experiences the presence of an effective magnetic field due to the magnetic moment of other spins. And we call this Weiss mean field, which is nothing but the exchange couplings of the neighboring spins relative to the spin on site I. So you sum over all the neighboring spin J around the site I of this Ising coupling term, which acts as if you applied an effective magnetic field on the site I. So same Weiss mean field will be present for all the other sites. You could actually use the same argument to show that for every site, the spin moment, every site will experience an effective magnetic field coming from their neighbors. So everybody has neighbors, and everybody affects everybody else. And so that's the so-called the Weiss mean field, which is kind of approximation. Of course, we know that the effect of this effective magnetic field should also include fluctuations beyond this mean field. So this is kind of a mean field approximation, which includes only the expectation value or the average spin moment after ensemble average. And of course, the effect goes beyond that mean field approximation. We need to also include the fluctuations beyond this mean field approximation. But that fluctuations turn out to be very small in some cases. As long as we are concerned or under the Weiss mean field approximation, we don't consider the fluctuations because they are neglected. Of course, these fluctuations will become important later on. But here, we simply just forget about all the other deviations from the mean field approximation. All right, so the Zeeman field includes both the external field and the Weiss mean field. So you need to add these two together. So therefore, for every site, the effective field is actually the external field plus the Weissman field contributions. But you know that what this is, the Sj is nothing but the magnetization on site J, which is considered to be uniform. And J is the uniformed Ising coupling, which we assume. And D is the dimensionality of the lattice, so we'll see later that under such a Weissman field theory, dimensionality doesn't play any role near the critical point. Okay, so the critical exponents do not depend on the dimensionality, which is certainly wrong. So dimensionality here only to take into account the number of neighbors, right? So we are talking about a one-dimensional Ising chain, then there are two neighbors, right? 2 times D is actually 2 for a one-dimensional. For a three-dimensional Ising system, there are 6 neighbors, right? There are just 6 neighbors. 1, 2, 3, 4, 5, 6. Okay, so it's 2 times 3 is actually your number of neighbors. And so that's the only place where the dimensionality comes into play, but it will not affect the critical exponents. So we could actually use the same method that we did for the free local spins to calculate magnetization by this taking first the free energy respect to this Weissman field, and you get hyperbolic tangent, which is more or less the same as that, except now we replace this external field by the Weissman field. Okay, so remember now the effective magnetic field should include both the external field and the Weissman field. But here is the tricky thing. So this M inside the hyperbolic tangent is the same magnetization on the left side of the equation here. So therefore, it is a self-consistent equation. So because the magnetization on the left-hand side is actually the average spin moment on every site, and that appears on the right side of the equation in the hyperbolic tangent, and which is exactly the same quantity as that on the left-hand side. So to determine the value of magnetization, we need to solve this equation simultaneously or iteratively or self-consistently, because the unknown variable appears on both sides of the equation, and the way that we solve this is actually the same as we did before for the infinite long-ranged Ising model. Remember that we plot these two functions. One is the straight line, another is the hyperbolic tangent function, and we look for the intersection between these two curves. And that is exactly what we are going to do. So in the limit of the zero external field, the magnetization can be non-zero in the zero temperature limit and zero field limit. And when that happens, we call this spontaneous magnetization. Remember, that's the essence of spontaneous symmetry breaking. So then we just do what we have done before. This is the magnetization, and this is y, and we have a line which shows y equals to m, and we have another curve which intersects with the yellow line, and this is y is actually hyperbolic tangent function. And again, there are in general 3 intersections, one at 0 and another is at plus or minus m0. So you see this mean field equation is exactly the same as that for infinite long-range Ising model. And therefore, these two methods are sort of equivalent to each other. So we have this situation where we have these 3 intersection points, and we also have a situation where we don't have an intersection. So that is the same as what we discussed earlier, that when temperature is less than Tc, you get non-zero intersections at plus and minus m0, which indicate the spontaneous magnetization. But when T is larger than Tc, there's only one solution, which is a trivial solution at 0 magnetization, and therefore the system does not order. And the Tc occurs exactly when 2dj divided by kb is actually Tc. So remember, this is what we call this beta j is actually 1 for this infinitely long-range Ising model. And here we simply just replace this infinitely long-range Ising model, j infinity Ising, by 2dj. So let me summarize. For t greater than Tc, m is 0, this is the disorder phase. And T less than Tc, M is finite, is a ferromagnetic state. And remember that this point at zero magnetization marked by the square is actually the unstable solution. And the 2 points at the finite magnetization is actually a stable solution. The unstable solution implies that as long as T is actually slightly less than Tc, you get solutions away from this zero magnetization, and that finite magnetization solution gives you a lower free energy than the zero magnetization solution. So that's the meaning of the unstable solution, because that point is not stable against a finite magnetization, which will lower the free energy. And on the other hand, these two finite magnetization solutions are stable because they are the lower energy states than the zero magnetization when temperature is less than Tc. So let's take a short break. When we come back, expand the magnetization near this Tc, and also we will get the equation of state, and then we could actually obtain the critical exponents that we already derived last time. So let's continue. First, a few lectures back, there's special correlation functions of the Ising chain, which goes e to the minus j log. Inside the log, the argument should be lambda 1 over lambda 2. So now we try to expand this equation of magnetization near the Tc. So the equation is given by this m equal to the hyperbolic tangent function. And inside the hyperbolic tangent, we have effective Weissman field plus the external field. So when this transition occurs, both the field, external field, and magnetization are very, very small. Remember that the spontaneous magnetization occurs when there is no external field, or the external field approaches zero, and at the same time, tiny little bit magnetization arises as an intersection of this hyperbolic tangent function and that straight line. Okay, so that intersection point could be as close to zero magnetization as possible near the transition. So near the transition, we assume, and this is the correct assumption, that the magnetization is actually very, very small. And so when both the external field and the magnetization are very small near the transition, we can Taylor expand this hyperbolic tangent function on both sides of the equation. And when we finish, we get this relation here. So we just keep this expansion up to third order in magnetization, and also up to cubic order in Tc over T. Okay, so we define a parameter called tau, which is Tc over T. When T goes Tc, tau is actually 1, which is dimensionless temperature. So this tau is very, very close to 1 when temperature approaches Tc. So of course, there are other terms which are neglected here, but it turns out that those terms are not important. So based on this so-called the equation of states, which relates the external field, temperature, and magnetization near the transition. So that's the equation of states near the transition, and we are able to determine the critical exponents based on this equation of states near the critical temperature. And when this critical temperature is reached, or critical points reached, the external field should be 0, and the temperature should actually go to Tc, but from a smaller value, T minus Tc, and temperature approaches to Tc from below. So you simply just plug in this condition. Here you get the spontaneous magnetization vanishes in that fashion. It's m squared is proportional to Tc minus T. So when T is less than Tc, this is positive. So you can see that if we approach the Tc from below, then this magnetization will vanish in the square root manner, proportional to Tc minus T. And this is precisely the definition of the critical exponent, which we call this beta, which tells us the power law dependence of the vanishing magnetization near this Ising transition. And based on this equation of state, you can easily see that this m is actually square root dependent on Tc minus T. And therefore, beta is 1/2. So this is the same value that we already derived last time based on the infinity range Ising model. Next, when we are exactly at the Tc, but in the presence of a small field, and there's another critical exponent called delta, which tells us the spontaneous magnetization near the transition as a function of the external field in a power law fashion, and this power law exponent is called delta, which says that this h is actually proportional to m to the power of delta. And by setting this condition at the critical temperature but the finite small field, and back to this equation of state, you could easily see that this field divided by kBt is actually proportional to magnetization to the power of 3, the cubic dependence on this magnetization. And this delta is actually 3, and it is the same delta that we found by this Toy model. So the last point is the calculation of this isothermal spin susceptibility, which is the derivative of the magnetization with respect to the external field at a constant temperature. And you can easily find this relation by taking this field derivative of the equation of state with respect to the field on both sides of the equation of states. Okay, so on the left-hand side, you get simply just 1 over kBt because that cancels with the derivative. And on the right-hand side, you get this chi t by definition, and also other function of chi t as function of m squared and also polynomial of tau. But we have in principle, two different exponents of this isothermal susceptibility, as a function of a t minus tc or tc minus t. So in principle, we may have two different exponents on both sides of the transition. So we call this gamma when t is larger than tc, and gamma prime when t is actually less than tc. So on both sides, this isothermal spin susceptibility diverges as 1 over t minus tc or tc minus t to the power of gamma or gamma prime. So based on this, we could easily evaluate this exponents gamma and gamma prime. So first, when t is larger than tc, then we know that there is no spontaneous magnetization, so n vanishes. As a result, look at this derivative of this equation of state with respect to the field. You see that this chi t is actually proportional 1 over t minus tc, and therefore gamma is 1. And likewise, for t is less than tc, you simply just plug in this finite magnetization as a function of a square root of tc minus t, we just obtained over there when beta is 1/2. And you plug in this temperature dependence of the magnetization back to this equation of state for this chi t, you get 1 over tc minus t dependence of the isothermal spin susceptibility. But remember, even though they have the same exponent, gamma prime is also 1, and it is the same as gamma, but the prefactors are different. So there is a factor of 1/2 or a factor of 2 difference in the prefactor in front of the chi t between these two cases, above or below tc, and which we'll come back to this point later. Let me summarize. Based on this D-dimensional Ising ferromagnetic model and also the Weissman field approximation, we are able to recover all the exponents that we obtained from this exactly solvable limit of the Ising model, namely the infinite long-range Ising model. And here you can see very clearly that those exponents do not depend on dimensionality. So they're just numbers which are independent of dimension d. Of course, we know from experiments and the more rigorous exact method that these critical exponents are different for different dimensional systems. The 2D Ising model and 3D Ising model certainly have different exponents near the transition. But here, the mean field theory doesn't tell. So which means that the mean field theory actually is accurate. It only estimates the critical exponents very crudely, very roughly. And in the next chapter, we will actually cure or try to actually take into account the fluctuations beyond the mean field to actually revise or correct this kind of a crude approximation of a Weissman field theory. But here, the first example that we could easily calculate the critical exponents for Ising transition based on either the exact or the mean field approximations. And this will serve as just a starting point to really address what happens near the transition based on our knowledge in statistical mechanics. So let's take a short break. When we come back, we will start to talk about these fluctuations in the mean field theory and the departure from the mean field theory and the beginning of the Landau's theory of a phase transition. So we continue. So now we start to introduce the concept of Landau theory for phase transition. So we will see Landau postulated kind of a Landau free energy, functional, as a function of this so-called order parameters, which is a very important concept in phase transition, which means that the ordered phase is a phase where we have non-zero order parameters. What are the order parameters? Well, in the Ising model, apparently the magnetization can actually serve as order parameter because remember, when t is less than Tc, you get a finite spontaneous magnetization. But this order parameter vanishes when t is above Tc. So apparently this scalar field, which we call this magnetization, again, it is a uniform mean field approximation that this magnetization is actually the same everywhere. However, we know that this magnetization field is also a site-dependent function. So it depends from point to point, from place to place. So in general, it is also the function of a real space variables. But here, we just simply consider this just a single scalar. And it is finite when we are ordered, and it is zero when we are disordered. And likewise, remember, there's an equivalence between the Ising transition and the liquid-gas transition that we showed earlier. So in the liquid-gas system, the order parameter is the density of the fluid, the density of a particle. Again, there is a critical density here, so there is a transition in terms of the particle number density between T below and above Tc. So this is the simplest possible order parameter, which allows us to distinguish the ordered from disordered states. But the scalar is just the simplest possible field that we could imagine to tell whether the system is ordered. And in a more realistic and more complicated models, this order parameter could be a vector, such as in the Heisenberg model, or the 2D XY magnet that we will introduce in just a moment. Then the order parameter, for example, in the Heisenberg model, described by this Heisenberg exchange coupling, Jij times this dotted Si to Sj vectors, where Si and Sj are n-dimensional, n-component spin vector. Of course, we are living in the three-dimensional world, so the number of components in the spin vector is just at maximum 3. But in general, mathematically, we could imagine that we can generalize the spin component to n component, which means that we can live in the world where the spin has an independent component. But that mathematical conjecture, but in general, we can have, for example, the Ising, there's just one component along the z-axis, right? 2D XY magnet where the spins lie in the plane and they could have just two components, right? In the Heisenberg limit, we have all three different components of a spin vector. So you can also calculate the spontaneous magnetization for the Heisenberg model by, again, calculating the expectation value of the vector Si after the ensemble average, and it is 0 when temperature is above Tc, and it is finite when T is less than Tc. But of course, when we have a multi-component magnetization, the spin moment will point to a particular direction in a multi-dimensional spin space. For example, in this case, the m vector may point to any direction in a three-dimensional space. And when that occurs, we call that the so-called ON symmetry is spontaneously broken. So in the disordered phase, the Heisenberg model shows so-called the ON symmetry, which is a symmetry that leaves this Hamiltonian invariant under a spin rotation. Suppose we have rotation of a spin vector on every side, and under such a spin rotation of an n-component spin vector, then the Hamiltonian of a Heisenberg model is still the same, because this is Si dot Sj, right? So when all the spin vector is simply just uniformly under a global rotation by an angle theta, then everybody actually is rotated by the same angle, then Si dot Sj is still the same, right? So you could actually show that mathematically, that under a spin rotation, the Heisenberg Hamiltonian is still invariant. But that invariance is broken. That symmetry is broken spontaneously when we are in the ordered phase. And for example, the simplest example of the Heisenberg spin model is the three-dimensional spin-spin interactions of a Heisenberg type, and that preserves the O3 symmetry. So we can also have two-component spin model called XY model. The XY model is the model that we have simply just XX coupling and YY coupling of the spin vector. So in other words, we don't have the Ising coupling here. Therefore, we have three different cases. The Ising case where we have only the Z component of spin that are coupled. And we have the XY magnet where only the spin coupled in the XY components. And we have a full Heisenberg limit where all the three components of spin vectors are coupled by the exchange couplings. Therefore, the spontaneous magnetization is a vector lying in the XY plane. So we have a spontaneous symmetry breaking of an XY model when D is actually larger than 2 and for n is actually greater than or equal to 2. So the dimensionality is somewhat different from the component of the spin. So n refers to spin component. Suppose the magnetization vector have only two components lying in the xy plane, then n is actually equal to 2. But still, the spin vector is actually living in the three-dimensional space, or the lattice is actually three-dimensional. So this refers to the dimensionality of a problem, but on each lattice point, the spin may have just two components. But these two component spin could actually cover all the three-dimensional lattice points. So you can have a three-dimensional XY model. You can also have a two-dimensional XY model or a one-dimensional XY model. So we have a spontaneous symmetry breaking of the XY model when dimensionality of your lattice is actually greater than 2, meaning for a three-dimensional XY model, we have the spontaneous symmetry breaking, but there's a special case when we have a two-component magnetization, but the lattice is also two-dimensional. Then when D and M both are 2, then this is a different transition called the KT transition. So the KT transition happens when we have a two-dimensional thin film of a superconductor at finite temperature. So we may generate the vortices, which is a topological excitation of a superconductor. And we may have so-called vortices and anti-vortices appearing at the finite temperature. And these vortex and anti-vortex actually form pairs at low temperature below the KT transition temperature. But above the KT transition temperature, these vortex anti-vortex pair are unbounded. So they can actually propagate, move freely when temperature is above KT transition temperature. And that transition is a very special transition, as we mentioned last time, that the correlation length usually diverges in a power law fashion as a function of what T minus Tc. But here in the KT transition, the correlation length actually diverges in an exponential way. And near the transition, the thermodynamics do not show the power law behaviors, but instead it is actually an exponential function. But still, it is kind of phase transition at finite temperature, and it is due to the topological excitations of your system, superfluid or superconductors, and it can be described by the XY model in 2D. Remember, in a few years back, in 2016, these two gentlemen, Kosterlitz and Solis, together with Duncan Haldane, share a Nobel Prize precisely because of this kind of a topological nature of a quantum matter. And then this kind of a KT transition is sort of the first study of this kind of a topological properties of quantum matter. Of course, there are other studies on the topological properties of fractional quantum Hall or integer quantum Hall effect and other graphene type of magnet, Ken Melee type of system, which shows the topological edge states of an insulator and so on and so forth. And these studies will lead to a very active research area today on the search for the topological phases of matter. So I'm hoping that at the very end of the semester, we will talk about this closest-solid transition. Unfortunately, when I was a PhD student, I took the advanced statistical mechanics from Professor Koslitz, and he himself explained the details of the KT transition in class, which is really a nice experience. And some of the notes that I use here come from his lecture notes. So in the sense that I'm giving you some lectures that Nobel Prize winner gave. So let's take a short break. When we come back, we will continue introducing the order parameters and then the concept of Landau's free energy functional. We introduced the concept of the order parameters as a scalar vector, but there is another type of the order parameter which describes the pairing between two particles, and that is the order parameter for a superfluid and a superconductor. So, for example, in the liquid helium-3, it is the well-known superfluid where the neutral particles in the superfluid state do not have a frictional, just dissipate any energy, so that the flow is actually dissipationless and without energy loss, and so we call this superfluid. And in the superfluid liquid helium-3 state, we have an order parameter which we call this psi, and this psi is a quantum mechanical object which describes liquid helium-3 particles, how they actually form pairs. So in essence, two such liquid helium-3 particles form pair, and the wave function which describes this kind of a superfluid pairing is called the order parameter of a superfluid, and which is anomalous kind of a pairing amplitude, which in quantum mechanical sense is product of the two wave functions, and these two wave functions effectively generate two particles at the same time, or destroy two particles. So we don't have time to discuss this superfluid pairing, but it just shows in the textbook that we have this 18 components of this order parameters, which consists of the orbital degrees of freedom, which is SO3 symmetry, and SO3 another describes the spin, which is a p wave kind of a dumbbell shape of the order parameter, and also the spatial wave function actually shows O2 symmetry. So it's a SO3 by SO3 by O2. So there are 3 times 3 times 2, it's actually 18 components. And there's another type of order parameter described how the electrons pair in the superconductor, and in ordinary metals, the electrons form Cooper pairs where two electrons can actually pair up in a singlet state, where one of the electrons actually carry momentum k and spin up, another carrying momentum minus k and spin down, and they live on the opposite side of the Fermi surface, and they form kind of a Cooper pair electron. And once they form pair, they are charged superfluid particles where you could have this supercurrent of charged particles floating around your superconductors, and there's no dissipation and no resistance and nothing. So the Cooper pair wave function is actually the product of the two Cooper pair electron wave functions, and it has two components. In an ordinary S-wave type of superconductor, where we could just use the amplitude and the phase to describe such S-wave superconductors as a product of these two wave functions of electrons when they form Cooper pairs. So these kind of three objects, order parameter for liquid helium-3 is actually looks very similar to the XY order parameter that we just discussed in the KT transition. So both systems are charge neutral state, but to the XY order parameter is somewhat similar, but different from the order parameters of S-wave superconductors. The difference is that in the superconductor we have charge, but in the 2D XY model it's actually charge neutral, just spin component matters. But a very crude approximation, order parameters describe how the particles pair in that ordered phase, especially when we talk about the Cooper pairs or superfluid pairing. In the XY model, we have this kind of a vortex-anti-vortex pair. So we may not have time to discuss the transition of this kind of a pairing of interacting particles, but this will be a topic of a quantum phase transition. This is just a setting up the stage of Landau's field theory. And Landau actually is really a genius theorist. He observed such similarities of phase transitions between the fluid and the Ising magnet, in the sense that we could actually describe the fluid transition by formulating free energy called Gibbs free energy, which describes the van der Waals equation of state by minimizing the Gibbs free energy with respect to this order parameter in the fluid transition, which is rho minus rho c, as I just defined over there. So in the fluid, we have a critical density. And once we reach that critical density at critical temperature, then we have a phase transition. And so the equation of state, which describes the fluid transition, is given by this equation here, where pi represents the critical ratio, P over Pc, the ratio relative to the critical pressure. And this pi is actually the function of the T minus Tc, or Tc minus T, and also a function of the order parameter, which is the rho minus rho c. When we are exactly at the transition, where rho is actually equal to rho c, and phi vanishes. But still, we can have equation of state. This pi plays a similar role as the magnetization in the Ising case. So we can actually construct this Gibbs free energy, which you could check our textbook or other references how to construct the Gibbs free energy, and based on the fluid dynamics. And here I define this nu, which is the, again, rho or rho c over rho, and pi is written in terms of those rho c over rho, and we could have such a equation of state, which is obtained by minimizing so-called Gibbs free energy of the system. But let's just look at the Ising model once more, because we just obtained such a equation of state, but we haven't constructed the free energy yet. So we could have this free energy, which describes the equation of state near the Ising transition in a very similar way that we construct the Gibbs free energy for the fluid transition. If we construct such a free energy, but again, this free energy is not the same as the Gibbs free energy, we will discuss the difference between so-called Landau's free energy and Gibbs free energy later. But let's just say that we can construct a function, a free energy-like function, which has this form, which is some kind of a constant. F0 is a function of temperature in the field, but it is independent of the order parameter, and some of the terms which can be expanded in terms of the powers of the order parameter, say m to the linear term, m squared term, m to the power of 4 term. So likewise, in the case of the fluid, the Gibbs free energy can be written in terms of the constant independent of the order parameter, and the order parameter to the linear term, and the quadratic term, and the quartic term. So you can see that these two free energies have exactly the same mathematical form, though the prefactors, this kind of coefficients are different, but you could always expand this kind of find such a free energy which can be expanded in terms of the powers of your order parameters. So that's the similarity that Landau discovered, that in all this phase transition, if they have exactly the same form of that free energy functional as a function of order parameters, and they should have the same critical exponents. And that is exactly what happened in these two cases, that we can find the same mathematical form of this free energy as function of order parameters, and by minimizing the free energy with respect to the order parameter, we get the equation of states, and from the equation of states, we get exponents. And you can see by comparing this equation of states between the fluid and the Ising model, and you see very much similar, and they can be cast in the same mathematical form, even though they have different coefficient and prefactor, and it doesn't matter concerning the critical exponent. So if you can actually show that in the case of the fluid, you can get the same exponents as the Ising magnet. So that's the starting point of the Landau's theory, which is based on a free energy functional as a power expansions of the order parameter. And the order parameters are very, very small near the transition, and therefore they could be expanded in power series in the free energy functional. And Landau observed such similarities, and he actually postulated a kind of expansion of the order parameter and constructed Landau's free energy functional. And Landau's free energy functional is not the same as any free energy that we are familiar with in the statistical mechanics. It's a new kind of free energy which is related to the Gibbs free energy, Helmholtz free energy, but they are not the same. So we will continue defining Landau's free energy functional in the powers of the order parameters in the next lectures, and we will see how to generalize this kind of model-dependent free energy function to a model-independent, more general Landau's free energy functional by considering just the symmetry and dimension of the system, and we are able to construct such a Landau's free energy functional, which describes the first order phase transition and second order phase transition and critical exponent and so on. See you next time.